Good morning, Astronomy 1010. As I mentioned in the email, I'm feeling a little sick today. I woke up with like a sore throat on one side of my neck and like swollen lymph nodes, and it's not fun. I'm not. I was gonna try to muscle through this lecture, but it's kind of hard to talk, and I think it's gonna just be a poor delivery. I know you guys love the live lecture, and I love giving it. But do you think maybe this one day we could just watch the video from last semester so I could rest up and maybe go get a COVID test next door? Is that something we think we can handle? Yeah, you feel okay about that? I know it's not ideal, but you know, there's nothing I can do about it, I guess. Unless anyone has any strong objections, I think that's going to be our plan. Okay. The trick is to find the proper lecture for us to watch. Now, before class started, I just looked at the lectures from last semester, and things are starting to deviate in terms of the numbering system. In last semester's lecture, it looks like lab 6 is still spectroscopy, which is what we want to do today. But it looked to me like lecture 7 was on the sun. So that means we either have to watch a lecture from one YouTube and watch a lab from a different one, or I could try to find the AS1020 the AS1020 lab and lecture and see if they kind of match with what we're trying to do. So I don't want to waste any more of your time than possible, because I know if you have to watch the video, you probably want to get the hell on it. But I'm sort of figuring this out as I go here, because I wasn't really sure what my plan was up until the last moment. I was trying to make it for you guys, but it's feeling like I'm not going to be able to do that. So AS1020, let's see here. I think this, even though it's for AS1020, is our ideal. I suspect it. So let me just slide along here, guys, and let me just make sure that this is the right stuff, okay? So what we have here is we have inverse square law, something I wanted to talk about, okay? That's a very important formula. Eventually, I should get into spectroscopy and the different types of spectra. That's a very important formula. I kind of go bonkers on it, okay? And then, no, this is not clear. Nope, this is one, I think this is one ahead. So let's go, oh, this is gonna be a fucking mess. I can just tell. Just bear with me, guys. So that was lecture 6, lab 6. Wow, I feel really, really stupid right now. So why is it on Austin's face and not mine? Okay. Just hold on, guys. Lecture 5, lab 5. This is probably it. Okay, yes. 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 Another good thing is this spectroscopy lab, I actually pulled it off a little better and more efficiently than last semester's. So I think this is our man here. I think the best lecture for us, because we did learn a little bit about atoms. Did we play Let's Build an Atom last time?
Yes.
Shit. All right. The problem is each semester kind of has its own like unique quirks. All right, maybe here's what we're gonna do. Maybe Maybe I'll see if I can get through this lecture for an hour and a half. I can't believe I'm thinking about doing this. And then you guys will watch the video for spectroscopy and let me off on half of it. How does that sound? Does that sound like a pretty decent trade-off? Because I'm just getting confused on how I want to do this here. Let me just pause the recording for a second. Okay, because I'm not entirely sure which is the best lecture right now to show you guys, I'm just going to give you the lecture that you should have today. And then you're going to watch the AS1020 video for spectroscopy, which I will include in the chat log, and I will include along with today's video. Let's do that now, ere I forget. It looks to me like AS1020 Lecture 5, Lab 5 is the ideal one. And it looks to me like spectroscopy starts right where you'd expect it, right around 140. Okay? All right. Yeah, around 143. So let's copy that link. And let's send it to the class chat log. I will also include this in the email to the class later. Okay. So why don't we try to muscle through a sucky lecture here, and we'll see just how good or bad it is. And then you guys will watch that video and do the lab without me. Deal? Do we have a deal? Okay, we have a deal. Last time you learned about the wave properties of light. We also probably should talk about the visible continuous spectrum and one of the experiments that Sir Isaac Newton did. Although Newton is famous for his law of gravitation and his laws of motion, he actually did some early and important studies in optics using one of these bad boys here, which is a prism. And it turns out that if you shine a beam of white light through a prism, you can make a rainbow. It might be kind of cute to see if we could do that here in class. Bear with me here. Hold on. I've got a bright source of white light here. I always think it's more jazzy to do a demonstration in person. Okay. Ooh. Let's see if we can pull this off. So here's a beam of white light. I'm going to try to shine this light through the prism. Ooh, here we go. And I want you guys to notice, I'm going to bring the camera way the heck up here. The trick is to get the rainbow without blowing out the light here. Can you guys see that? It would be a lot more helpful if I collimated the beam of light. I'd have to pass it through a thin slot, but I don't really have a good collimator on hand right now. Notice that you can kind of see a sucky little rainbow appearing there. This demo worked a lot better in person because I used to use a transparency projector for this demo, and that is 4 times the wattage of this, so the rainbow would be really, really bright. It also helps to focus and collimate the light into a narrow beam. Otherwise, white light is kind of scattering around and washing out the prism, which is what was happening to me. But let's just take a look at this in cartoon form so that you can understand what happens there. I need to grab a slide, which I didn't open because this was sort of a chaotic beginning to our class today. Astronomy. Let's go with 1020. 1020, slightly better slides. All right. So what you can see is in this animation, number 18, you can see a beam of white light, which they did better than me. They collimated it into a narrow beam. And when it strikes the glass, something that we call dispersion happens. It's also known as refraction. Light, when it hits the glass, bends, and the angle of bendiness depends upon the wavelength of light, which is sort of the same thing as color. So you can see that white light will be separated into a rainbow, and the order of the colors is very particular. It looks like this. Newton was the first person to turn white light into a rainbow, and he kind of had to take a moment to think about what was going on. He wasn't sure at first if the glass was just transforming white into a different color, or if that white contained all of the colors. And he did a very clever experiment to sort of prove to himself that white light contained all the colors. What he did is he put the rainbow back against a prism and discovered he could recollapse it into a white beam. And that told him that the white beam contained all of those colors. This is now what is known as the visible continuous spectrum. It's continuous because it has absolutely no breaks. It's a smooth gradient of color, and the order of the color is always the same. Violet, in Newton's day, this color was called indigo. Blue referred to only sky blue. So dark blue was actually called indigo back in the day. I've got a personal crusade to bring back the term indigo. Then there was green, then a narrow band of yellow, and then orange, and then red. Oops. It makes an acronym. If you do it in the reverse direction, because you can make the rainbow go in either direction, people often know it by the nickname Roy G. Biv. But I'm kind of funny and weird, so I prefer Bib G. Yor, because what you'll notice is that the colors each correspond to a different wavelength of light. And this is what is known as the continuous visible spectrum. It looks like I'm going to have to open that Logitech control panel because I've got some funny focus issues. Testing, can you guys hear me? My microphone stopped working for a second. I fucking hate this Logitech camera. Logitech, if you ever listen to these videos, you suck. Do better, okay? Don't make me install your lame ass update every single time. It doesn't change. Okay. Ugh. Don't get me started on this. Let's take some notes. Sorry, it's making me install this fucking thing again. It's so irritating. Okay. So let's talk about light. Um, did we define light in the past as a electromagnetic wave? Did we do that? Do you have notes on that, Jetta or Kim or John? We did do that part, right? Okay. So light, we'll just kind of write it again. It's an electromagnetic wave. And light is comprised of photons. I think a very good analogy is that photons are to light as atoms are to matter. We know that matter is made up of indivisible units called atoms, and light is made up of individual little bits called photons. Photons can have long or short wavelengths. Um, Photons are kind of like, you can think of them as particles of light or as waves. They have something called wave-particle duality. Sometimes people like to think about them as packets of light. They can be tiny or they can be really effing huge, okay? If I were to draw a picture of a photon in my mind, it would be of like a localized wiggle. Do you guys remember this is the electromagnetic field? It's the field associated with positive and negative charges, like protons and electrons, okay? So this is a picture of a little photon. These photons have properties like wavelength, frequency, and energy, okay? And how do I want to say this here? Wavelength kind of corresponds to color. What Newton did with white light when he passed it through that prism is he took the world's first ever spectrum, okay? So if you take white light and you pass it into a prism, that prism will separate it into a rainbow. And what you guys used to call the rainbow will now be known as the continuous visible spectrum. Shit. Wow, you can tell I'm having a bad day already. How's that look? Like crap, I know. All right, so the continuous visible spectrum is basically another term for the rainbow. And it turns out there are other types of light besides visible light, but this is the type of light your eye can see. You can see this light. And let's draw a little model of it, okay? I have some colors here. If you have colors handy, that could be nice. I use the acronym VIBGYOR. I'll use blue for indigo and for cyan. Well, let's turn a little bit of light here. The nurse on duty has made me some lemon ginger tea, so. All right. Vib G for green. And I don't have a yellow marker, so I'll have to go yellow, orange, red. You'll be looking at the visible continuous spectrum in lab today when you watch the pre-recorded version. Some things that I want you to know. By the way, that's violet, but it looks kind of black on the camera there. Red has a wavelength of 700 nanometers, and violet has a wavelength of 400 nanometers. So wavelength is increasing from purple towards red, okay? You'll remember that we use the Greek letter lambda for wavelength. Wow, I really wish more people were sharing video today, but it almost really justifies that pre-recorded lecture more than ever. What a difficult day to be sick. I want to hide the trolls because I find you offensive. Okay, hide non-video participants. Okay, There we go. I'm going to erase this. Let's talk about a spectrum. A spectrum is something you're going to be looking at different versions of in today's class. A spectrum happens when you break light into its component. And honestly, we could say a bunch of different things here. I could say wavelengths. I could say frequencies. I could say energies. Or I could say colors. And in a way, all of these things mean the same thing. If I tell you that a laser emits green light with a wavelength of 532 nanometers, that uniquely specifies the wavelength, the frequency, the energy, and the color, which is a cool, groovy electric green. Here, let's give you some electric green. All right. Why are these things the same thing? Because of those formulas that you learned in your last class. Speed of light is wavelength times frequency. That formula relates wavelength and frequency and pegs them 1 to 1. The energy of a photon is Planck's constant times the frequency. That pegs energy to frequency. And the energy of a photon can also be written as hc over lambda. Those are formulas that we used in our homeworks last time. We also, well, we learned them last time, and then we used them in our homeworks last time. You'll be using them for homework again on Wednesday. Hopefully I'll be feeling a little better then, so you don't get me at my worst. Today, there is a cottage industry called spectroscopy, which is what you're going to do in your lab today. And spectroscopy is analyzing different types of spectra, okay? Is where you analyze different types of spectra. It's going to turn out that there's 3 basic types of spectra, and I want to talk about them before we get to our lab today. There's 3 basic types. Usually, when you analyze different types of spectra, I should mention that you can learn about the atoms or the material that's emitting that light. You learn about the matter that is emitting light. At this point, I'd like to take a little kids break to just kind of go over some different terms. I will not be taking notes on these, but I think it might be good to like have a quick chat about it. It's the different ways that light can interact with matter. I used to think this picture was stupid. It's in your book, but over time I realized that it actually could be helpful if you're just taking your first step into the world of light to learn that there are different terms that we use. They all have very specific meanings. There are things in nature which are emitters of light. Emitters of light would be the sun, a light bulb, a laser, your iPad screen, a glowworm, a lightning bolt. Not everything emits light, but some things can and do emit light. Coals in a fire. Once light is emitted, it goes bouncing around the world. It can be absorbed, say by the ground, and it can heat up a rock in the Sonora Desert. It can be scattered off the ground, like when light scatters off of white snow and you get snow blindness. In general, all materials absorb a certain fraction of light and scatter a certain fraction of light. Even a black jacket, which is supposed to absorb all the light, will usually backscatter at least 10% of the photons that hit it. And you can see that in the form of highlights when you look at your felt blazer or something like that. There's really no such thing as a truly completely black substance, nor is there any such thing as a completely white substance. They all have degrees of reflection and absorption. In addition to reflection and absorption, light can sometimes be transmitted through materials. Visible light, of course, is transmitted through glass, which is why you can look out your window. It turns out that different types of light that we're going to learn about can be transmitted through, like, for instance, radio waves. For radio waves, an entire house would be made of glass because it can pass through walls and it can pass through your body without blocking any of the photons. More on that in a bit. Light can also be reflected off of surfaces like mirrors. There's a slight difference between reflection and scattering. When you scatter a photon, scattering means it bounces in all crazy directions in every which way. But reflecting preserves the one-to-one geometry of the inside ray and the entrance ray and the exit ray. And that's how you can see a picture of what you're looking at on the other side, is because the geometry and the angles of all the light is the same. You don't really need to worry about understanding all of these nuances. I just want to talk a little bit today about emitters of light and how we can get different types of spectra. And we'll get into some of this stuff next time, okay? So let's learn about where photons are born. Let's start there. I'm going to erase this, if that's okay. All light, for the most, well, okay, most light is born inside of atoms. Light is created by atoms or by charged particles. Like, for instance, a free electron or a free proton. And let's take a look at something called the energy levels. Or the electron orbits in a hydrogen atom. Okay? So, do you guys remember what the composition of a hydrogen atom is? Who's educated? Who knows what's up?
Is it just one proton and one electron?
That's right. So let's start by drawing that. Nicely done, Jenna. Now, the electron is in orbit around the proton. And when the atom is cold, when the atom is in its sort of resting state or its natural state, let me adjust the glare here. It's bothering me. When the electron is in its default orbit, it's known as the ground state. And the ground state is basically the lowest orbit. We can also think of it having the lowest potential energy. You guys remember that if you lift a brick up off the ground, you create gravitational potential energy. Atoms also have a version of this, but it's electrostatic potential energy. The electron is actually attracted to the proton, just like bricks are attracted to the ground. And if the electron orbits at different distances, it can have different energy levels. Now, the distance that the electron orbits from the proton in the ground state is something like 0.05 nanometers. Do you guys remember what a nanometer is? Sometimes we measure these distances in nanometers. Sometimes we measure them in a unit called angstroms. Angstroms are an old-fashioned unit. What the hell is a nanometer, class? Prove that you remember stuff.
1 times 10 to the negative 9th meters.
So 1 nanometer is 1 times 10 to the minus 9 meters, right? Today during our labs, you will be using a unit called the angstrom. The angstrom is kind of like old-fashioned. We don't use it so much anymore, but astronomers still like to use it. The angstrom is 1 times 10 to the minus 10 meters, or 1 angstrom is 0.1 nanometers, right? 1 nanometer is 10 angstroms. It is possible to take the electron and energize it and move it into a different orbit. But here's where the baby solar system model of the atom starts to break down. When Earth is orbiting around the sun, it orbits at a distance of 1 AU. You learned that already. But there's nothing in the laws of physics that would have prevented Earth from forming a little bit closer to the sun or a little bit farther away. For instance, Venus orbits at 0.723 AU. And if you could take the finger of God and you could push on the Earth, in theory, it would be possible to make the Earth orbit at 1.111 AU if you wanted to. Electrons do not work like planets because you're getting down to the fundamental resolution of space itself. So here I'm going to use some $10 words over here on the side. I'm going to tell you that the orbits of electrons are, and here I can use a bunch of different words. The real word is quantized. That's how we say it in physics. Quantized means it comes in discrete, unique packets. Other words that we could use in place are discrete. I could use the word choppy. And maybe even in a more modern sense, I could say pixelated. Those are all different things that kind of capture the essence of quantization. For instance, if you could heat up this hydrogen atom, say by giving it a kick, punching it in the face with another atom, smashing it into another atom, you can get the electron to jump up to another orbit. And that second orbit is called the first excited state. And there's a low orbit, the ground orbit, there's a first excited orbit, there's a second orbit, a third orbit. But at this point, it becomes easier to keep track of them by assigning them what's called a quantum number. So what we do is we call the ground state the n equals 1 state. We call the second orbit the n equals 2 state. We call the third orbit the n equals 3 state. And there's a fourth orbit, and a fifth orbit, and a sixth orbit. My art skills are limited, so here it might be nice to look at a diagram. I'm going to show you two different diagrams. Now, the real picture of what's going on looks like this. Here you can see the first orbit of the electron, the second orbit, and they're all at kind of pre-proscribed distances. In other words, the electron can orbit here on this path, the electron can orbit on that path, and the electron can orbit on this path, but in between is kind of a no man's land. It's actually impossible for the electron to maintain a stable orbit at these distances in between. It can quickly jump from one orbit to another, but it cannot hang around in between for any extended length of time. These orbits are stable, in between is not. Because it gets annoying to represent them as circles, it's customary to represent these orbits with something called an energy level diagram. And this energy level diagram is kind of an abstract representation of the different orbits the electron can have. When the electron is in the ground state at n equals 1, we call that the lowest state, and we assign it an energy of 0 electron volts. You guys will remember that electron volts are a tiny little packet of energy. 1 eV is equivalent to 1.6 times 10 to the negative 19 joules. Fuck, I hate trying to draw with a mouse. Okay. Not too bad. So that's 1.6 times 10 to the minus 19 joules. I'll probably write that down at some point. Obviously, it's a little more elegant to work in units of electron volts than it is in joules. In order to get an electron to jump from the lowest orbit to the first excited state, the n equals 2 state, you've got to give that electron exactly 10.2 electron volts. And if you give it another kick of energy, say another 1.9 electron volts, you can kick it up to level 3. Now, I want you to notice something. There's a level 4, there's a level 5, 6, 7, 8. There's actually an infinite number of levels, but as the orbits get higher and higher, they start to kind of blend together into a smooth gradient. And the highest energy an electron can have in a hydrogen atom is 13.6 electron volts. That's known as the ionization potential of hydrogen. If you give an electron in the ground state more than 13.6 electron volts, boop, you can pop it right off the atom, and you now have ionized the atom. Can you guys remind the class what ionized means from your last lecture while I sip tea? Come on, guys, play with me. I'm literally dying for your education here.
I found
Anna?
it. Sorry, it was in to remove or add an electron.
In this case, it would be to remove it if you gave it 13.6, right?
Mm-hmm.
Okay. Okay. Let's talk about how we raise and lower these electrons in their orbits. Okay. Let's talk about this. There are two ways to raise an electron orbit. Means to go from a lower to a higher orbit. Method number 1 is smash it with another atom. That's a version of basically conduction. Okay? That's a heat transfer method called conduction. And the second is to hit it with a photon of unique energy and wavelength. And that's a process called absorption. However, something happens when the electron drops from high orbit to low orbit. When the electron drops from high to low orbit. Okay, here I'm going to wave my hands a little bit and tell you that there is some crap that's in today's lecture that's unfortunately over your pay grade. You're not ready to learn all of the details at once. But let me tell you that when an electron gets kicked up to one of these excited states, when you excite an atom, the electrons tend to orbit around the nucleus for a period of time that's usually something like 10 to the minus 5 seconds. So that's how long the electron will stay in an excited state. Now, 10 to the minus 5 seconds is a short period of time for you. But in the world of atoms, that's actually a long time. An electron could probably orbit the nucleus more than 50,000 times in 10 to the minus 5 seconds. So that's quite a few passes before it has to drop back down. Usually what happens, all right, here's where I'm going to lie to you because I don't really know the answer. The electron gets tired after 10 to the minus 5 seconds, and it will spontaneously drop from high to low orbit. If it's in the second state, or if it's in the n equals 2 state, it will drop to the n equals 1 state. If it's up here, it can do a bunch of different things. It can drop one by one. We call that a cascade. Or it can just skip all the other levels and drop right back to the bottom. When that happens, the electron is going to drop, lower its energy, and release that energy in the form of light, or a little photon. And that's where all light is born, inside little factories of atoms. When an electron drops from high to low orbit, it emits a photon of unique wavelength, frequency, and energy. And that photon, this process is called emission, and that photon is known as an emission line. Let's draw a picture of this to try to help you understand what's going on. Here's the high orbit, here's the low orbit, okay. I'm not going to put any particular numbers on them because many different transitions are possible. The electron will drop from high to low orbit, and as it does this drop, it will emit a little photon of unique wavelength, frequency, and energy. And that's your emission line right there. In your lab today, you're going to be studying emission lines from different atoms. Each atom produces multiple emission lines that depend upon the details of its orbits. We're going to try to calculate an emission line, and then I'm going to show you some examples of emission lines. Okay, and then we're going to talk about Kirchoff's laws. I think we can do all of that in the remaining time. Let's start with the calculation first. I'd like to draw a new picture now. I'm going to erase here. All right. Let's go over a single transition that I think is particularly interesting. It's known as the 3-to-2 transition of hydrogen. Or the 3-to-2 transition of a hydrogen atom. Now, at the start of our story, I have a proton. The n equals 1 state is empty. The n equals 2 state is empty. but we find our electron at the beginning of our tail in the n equals 3 state. And the electron has been orbiting around in the n equals 3 state for about 10 to the minus 5 seconds or so. And in that time, it's gotten tired, and it will drop from n equals 3 down to n equals 2. It could have dropped to n equals 1, but this particular electron on this particular day was feeling kind of funny, so it dropped from n equals 3 to n equals 2. And it emits a photon of unique wavelength and energy. Now, we're going to try to calculate the wavelength of this photon. Find the wavelength of the so-called emission line. How is it possible for us to do this? Well, we know that because of the conservation of energy, that the energy that the electron lost in the drop must be equal exactly to the energy of the photon emitted. This is a key point which should make sense to you guys. If you drop the electron from this orbit to that orbit, it's going to lose potential energy, and that energy to be conserved must be emitted in the form of a photon. You know, that's not too much difference than what happens with gravitational potential energy. You know, if I lift up this meter stick, I create gravitational potential energy in Earth's gravitational field. And when I drop the meter stick, energy is released. Where do you think that energy went? We know where it came from, right? I had some Indian food for breakfast, and that's where I got my muscle energy to pick the ruler up. But John, where would the energy go once you drop it?
It dispersed out. It didn't hit the ground. It didn't go up.
But what form did it take when it dispersed out? I was trying to give you a hint. Let me give you a better hint.
A sound?
Exactly, right? If you analyzed with a decibel meter the energy in that sound wave, you would find that it's almost exactly equal to the potential energy of lifting the ruler up to that particular height. So it shouldn't be too weird that a light wave will come out of atoms here. Sound waves, of course, sound and light are not the same thing, right? Sound is a push of air molecules, but it has wave-like properties, just like photons do. I just wanted to show you that there are kind of analogies between electrostatic potential energy and gravitational potential energy. All right. We know that the energy of the drop must be equal to the energy of the photon. And the energy of the drop basically means the difference, the change in energy, or in our case, E3 minus E2. Why don't you guys look at my how much energy will the photon have if the electron drops from orbit 3 to orbit 2?
.9.
0.9? Jenna?
1.9.
1.9. Now, this is a somewhat crude picture here. I'm going to tell you the actual answer, I believe, is 1.895 electron volts. That's for the difference between energy 3 and energy 2. It rounds up to 1.9, but we're going to need 4 significant figures for what I'm trying to do today. Now, we know that this has to be equal to the energy of the photon. I'm going to calculate the wavelength using those formulas from last class, but first let's convert it to joules. I'm going to do this for you in the interest of time. 1.895 EV. To go from EV to joules, 1 electron volt is 1.6 times 10 to the negative 19 joules. Why don't you guys calculate that for me while I grab some drink? Whew. Hey, can you give this like 30 seconds to the microwave for me? I'm getting through. Sorry? No, I'm not going to do the lab. I'm going to farm it out. I'm going to farm it out to pass me. What you guys got?
I got 3.032 times 10 to the negative 19th joules.
Great. Let's just keep 3.03. Okay. Which formula do I want to use to find the wavelength? Can you guys tell me?
C equals wavelength times frequency.
But we don't have the frequency, Jenna. We have the energy. This is the energy, right?
Oh, yeah. So E equals H times C over wavelength.
Good. And you know how to rearrange that, right, Jenna? How do I rearrange that formula?
E times,
No. Wavelength is
yeah,
in the bottom. Flip it up to the top.
wavelength times energy.
Okay, but now flip the energy onto the bottom.
Okay. So H times C over energy.
Yes. What you did is you flipped the wavelength across the equal sign to the top, and you flipped the energy across the equal sign to the bottom, right? If you can flip a burger, you can flip an equation. It takes the exact same amount of brain power. Today we're going to use a slightly more advanced version of Planck's constant. I think I'm going to want to keep 3 sig figs. Planck's constant, I believe, is 6.63 times 10 to the minus 7. Who saw Stranger Things and knows the Planck's constant? 6.63 times 10 to the negative 34. We usually use 7, but today we have to do something a little more precise. The units are joule seconds. Times the speed of light. Believe it or not, the speed of light is good to 3 significant figures at 3 times 10 to the 8 meters per second. And that's all divided by the energy. .03 times 10 to the negative 19 joules. Okay, punch them up while I sip the tea. What you got?
Um, 6.6 times 10 to the negative 7.
Give me 3 sig figs, actually.
Okay, 6.56 times 10 to the negative 7.
What are my units, Jenna?
Right. Hold on one second. I just want to figure it out. Is it meters?
Correct, because it's a wavelength. How many nanometers is that? You guys suck at dimensional analysis, right? I can't trust you. I can't trust that you learned this. Or you want to prove me wrong. How many nanometers is that?
Like 6 or 7?
No. Yes, you do suck at dimensional analysis, okay? We multiply by a division bar. I don't know why you suck at it. It seems to be like the only thing that's consistent from lecture to lecture. You know that 1 nanometer is 1 times 10 to the negative 9 meters. Do it right. Tell me what the real answer is.
Mm. 656
Units?
nanometers.
What color is this?
Like an orangey red, basically red.
Wow, you're good. I'm impressed with you. .656 nanometers, you can see, is quite red. This is a very magical photon in astronomy. It's a red photon, and it has its own name, hydrogen alpha. So it's red, and it goes by the name hydrogen alpha, one of the most famous photons in all of astronomy. That's right, there are famous photons, just like there are famous people. Let me tell you a story about where you might find hydrogen alpha. Somewhere out in deep space is a giant cloud of hydrogen gas known as the Rosette Nebula. And this hydrogen gas is surrounding a cluster of newborn stars which pump out a lot of intense radiation. This radiation tends to heat up the surrounding hydrogen gas. I want the astronomy picture of the day. Do you guys see all of that red light coming from this beautiful nebula? All of that red light is created when electrons in different hydrogen atoms all simultaneously drop from orbit 3 to orbit 2 and emit a very unique piercing red light, hydrogen alpha, a beautiful red color that gives this emission nebula its name. In astronomy, we call them emission nebula because they are powered by the process of emission. When electrons in a high orbit, the n equals 3 state, drop down to the n equals 2 state and emit a photon of unique energy. In that sense, the Rosette Nebula, as it's called, is kind of like a laser nebula. It's emitting a very pure color of very, very unique light at an exactly precise wavelength. And this is just one of the possible emission lines that hydrogen can produce. Where's my damned hydrogen atom? Okay. You just calculated this line here, hydrogen alpha. That's caused by the 3 to 2 transition. According to my energy level diagram seen above, you can see that there is also a blue line that's emitted by hydrogen, which we call hydrogen beta. Can you guys look at the chart and tell me which transition is responsible for producing hydrogen beta?
Level 4 to level 2.
Right. So you can see 4 to 2 has an energy drop, which if computed into a wavelength like we just did, would be 486 nanometers. There's also a purple line called hydrogen gamma. This one's not going to come out too well during the video today, but I'll show it to you. That's created by the 5 to 2 transition. There are other transitions that produce other types of light that are not in the visible spectrum, and I'll talk about that in a moment. By the way, what do you think hydrogen, what color will it be if you mix all of these together? If you take a glowing hydrogen lamp and you mix red, blue, and purple together, what color do you suspect will result? Take a guess.
Like,
Sorry? No, it will not produce white because it will not be all the colors of the rainbow. What about your color theory class? Ever play with crayons? What does red plus blue create?
Purple,
Purple. And then purple plus purple makes
indigo.
probably purple. Purple plus purple equals purple. That's color math for you, okay? During today's lab, I will take some of this stuff, a tube of pure hydrogen gas, and I will stick it into one of these bad boys, a power supply, and I will heat up that gas by passing a current of electricity through it. And shit, this doesn't have a 3-prong charger. Ugh, I want to die. Okay. Here's what we'll do. I'll take you on a tour. Can you all hear me? Pretty. Y'all see that? Cool. Suppose I were to heat up helium. Do you think helium would have the same emission lines, or would it have different emission lines?
Different.
Yeah. It turns out that each atom has different energy jumps. And so each atom has its own unique set of emission lines. And that's one of the things we'll be doing today. First, I need to talk to you guys a little bit more about spectra before we can get there. Okay, actually, let's write down what we just learned here, okay? So we just learned something about the hydrogen spectrum. The hydrogen spectrum, in the visible portion of the spectrum, which is all we've really talked about yet, looks something like this. It's sort of like Newton breaking it into a rainbow, but instead of a rainbow, only 3 colors appear. There is a violet line at 434 nanometers. That has the nickname hydrogen gamma. There is a blue line at 486 nanometers. That has the nickname hydrogen beta. And there is a red line at 656 nanometers. That's the one that we calculated. And that's called hydrogen alpha. That's also related to the color of the Rosette Nebula. That's kind of a cool astronomy tie-in for you, to give you a sense of where we're going with this. In general, we can also write that each atom on the periodic table emits a unique set of emission lines and that's known as an atom's emission line spectrum. An emission line spectrum is fundamentally different than the rainbow. Okay. I want you guys to look down below. Well, it will be possible for me to show you today an emission line spectrum. It takes more elaborate sort of setups and demonstrations to produce the bottom one. This is an emission line spectrum for hydrogen. And down here, you see an example of something called an absorption line spectrum. An absorption line spectrum is when you have a complete rainbow, but then there are narrow gaps where photons have been removed from the spectrum. Notice that those gaps exactly correspond to the emission lines. What's happening there? You might be able to guess. The electron is starting in a lower orbit. White light of all different colors is hitting the atom, but the electron can grab this photon at exactly 656 nanometers and absorb that energy to jump up to a higher level, removing that photon from the white light spectrum. This type of spectrum, which is almost like white light, is called an absorption line spectrum. In the 1800s, probably the late 1800s, there was a very serious looking fellow named, get rid of this thing, named Gustav Kirchoff. He was a Prussian scientist, and I just want to show you his Wikipedia illustration because, or it's actually an old daguerreotype. He just looks pretty awesome. Now this is going to be my, I really want this to be my 2021 look right here. All right, 18th century mad scientist. This famous scientist, Gustav Kirchoff, studied light from different light emitting sources and used prisms to break them into their different components. And he basically discovered that there were 3 different types of spectra found in nature. What are those types of spectra? The following cartoon will demonstrate. Oops, it's too high up. If you take a light bulb or a star, it usually produces something like white light, which is a rainbow spectrum or a continuous spectrum. If you take gases of a pure atom, you can either get an emission line spectrum if you heat it up, or if the hydrogen gas is cold and very thin, you can pass white light through it and you can create an absorption spectrum. It's very difficult to create a good absorption spectrum with those hydrogen gas tubes because the gas needs to be very cold and room temperature is not cold enough to create the absorption spectrum. So I have a difficult time doing that in the lab today, as you will discover. I end up showing you a different type of an absorption spectrum, so I'll save that as a surprise. Kirchoff came up with what are known as Kirchoff's 3 laws of radiation. And it's kind of like the rule book for how spectroscopy works and how different types of matter produce different types of spectra. Let's write those laws down. These are known as Kirchoff's 3 laws of radiation. The first law is the law of black bodies. The law of black bodies states a hot, dense solid produces a continuous spectrum. Remember that continuous spectrum is code for rainbow. Hey, Jordan, you think you could get me some ice water? I have a fearsome thirst. All right, a continuous spectrum or rainbow. I want to add a note. I want to make my own humble contribution to Kirchoff's laws. That's how outrageous I am. I would like to also make a note. Depends on the temperature, not on the element or atom. So those rainbows that you saw me trying to make today with the lamp will not be different for hydrogen or helium. It just depends on it being very solid and dense and hot. Thank you. All right. Second law is the law of emission. The law of emission states that a hot, thin gas produces an emission line spectrum. This does depend on atom. The third law is the law of absorption. This one's the most irritating for me to write. A cold, thin gas in front of a black body produces an absorption line spectrum. And obviously this depends upon the atom as well. Today, I'll be trying to show you different types of these during our laboratory session. Okay? You guys got that? You're pretty fast writers, I think so. Okay. I'm going to do one last thing before I stop and turn you over to past me, because this has been hurting me, my throat a little bit. Guys, I really hope I can get some more people to join in these live sessions here. I guess I've got 9 participants. I don't know why everyone's sort of in the dark on me today. But seeing as I'm sick, I forgive them. I want to talk about the fact that there's other types of light besides visible light. And that's because it'll come in handy for next class. So now that you've learned a little bit about light and spectra, I want to introduce to you something called the entire electromagnetic spectrum. This includes all the different types of light that is found in nature. Your eyeballs are sensitive to a pitifully narrow range of electromagnetic radiation from 400 nanometers wavelength, which you call purple, to 700 nanometers wavelength, which you call red. But there are other wavelengths as well. There's infrared light, which is emitted by your body and emitted by remote controls that turn on televisions. There's also toaster ovens emit infrared light. At longer wavelengths, there are radio waves, which are transmitted from towers to your car radio. At shorter than violet wavelengths are ultraviolet wavelengths. These give you a sunburn at the beach. X-rays are used in medical imaging. And these very, very short wavelength gamma rays are crazy bad for you. They come from nuclear explosions and power plants, and they can irradiate you and turn you into a teenage mutant ninja turtle. Bad business absorbing gamma rays, okay? Let's make a little map of this because I expect you guys to memorize this. So this will be our final note for the day. And then I'm going to turn you over to a YouTube video to watch and do my lab, okay? Okay. Let's draw the electromagnetic spectrum. It's the totality of all the light that exists in nature. In a way, the electromagnetic spectrum is kind of like the periodic table for elements, except it's for photons instead. In the middle of the scale, we have the type of light that your eyes are sensitive to. It's actually quite thin, but I'm magnifying it for illustration purposes. This is the visible, sometimes it's also called the optical regime. Oftentimes, astronomers refer to these things as regimes of the electromagnetic spectrum. A regime is kind of like a zone or a kingdom or something, right? Visible includes the VIBGYOR spectrum. VIB G Three good reference numbers to remember is that red is 700 nanometers, violet is 400 nanometers, and green is about 500 nanometers. This is why nanometers are a nice, cute unit, because it's easy to memorize the numbers for visible light. At longer wavelengths, we have infrared. Infrared usually starts somewhere around 1,000 nanometers or 1 micron, and goes all the way up to wavelengths around 1 millimeter or so. Somewhere around 1 millimeter, this much longer light turns into radio light, the sort that's emitted from radio towers. Ultraviolet radiation otherwise known as UV. Sometimes the infrared is just referred to as IR. Those are nicknames. Goes from 400 nanometers down to about 10 nanometers. Then we have X-rays. X-rays are damaging to your cells, but mostly we use them in technology to bounce off your bone. X-rays can pass through the flesh of your muscle, but it bounces back more frequently off of bones. That's why you can take an image of your skeleton using X-rays. They are bad for you, which is why you usually have to cover up your private parts with lead, blankets, so that you're not irradiating your genitals. People tend to not like that sort of thing. Okay. Somewhere around 0.01 nanometers, you get into a very short but deadly type of light called gamma rays. So this is the gamma ray spectrum. And as I mentioned, gamma rays are usually found as a result of nuclear reactions. X-rays too, but definitely gamma rays are almost always from nuclear reactions. All of this stuff is the same stuff. It's all light. And you guys will remember that when I introduced light before our spring break, I told you that light was an electromagnetic wave. And the only difference between one type of a light and the other type of a light is its wavelength, the distance from crest to crest of your wave. But I've got to tell you, the different forms of light all behave very, very different from one another. They each have their own psychology. So remember that in this chart, wavelength is increasing to the right, but that energy increases to the left. Gamma rays fundamentally have more energy than radio waves. By the way, there's a range in between infrared and radio, sometimes known as the microwave regime. People who think microwaves nuclear irradiate their food are confused people who do not understand the difference between gamma rays and X-rays, which are harmful radiation, and microwave radiation, which, although it could heat up the water in your skin, is harmless in low doses and very effective at heating up water. Radio waves and infrared usually, well, infrared light can kind of heat up your toast, right? Radio waves don't have enough energy to heat up anything. They just pass right through you. Astronomers actually work in different zones of the electromagnetic spectrum. By looking at something like the Rosette Nebula in a different wave band, in a different regime, you can learn different things about the physics. So for instance, for my final point, I want you to consider the 2-to-1 transition of a hydrogen atom. Class, what wavelength of light is released when an electron drops from level 2 to level 1 in a hydrogen atom? What wavelength of light is produced? What wavelength photon is produced when an electron drops from orbit 2 to orbit 1 in a hydrogen atom?
Are you talking like an infrared?
I just want the fucking number. I want you to read the number off the chart.
121.6
Units.
nanometers.
And what regime of the electromagnetic spectrum is that?
Ultraviolet.
Very good. It's shorter than violet, so it is ultraviolet. It's down here. What that suggests to me is that if I look at the Rosette Nebula in the optical regime, I'll see hydrogen alpha, which is the 3-to-2 transition. But watch what happens when I look up Rosette Nebula as imaged with an ultraviolet telescope. Now, the red hydrogen alpha lines have disappeared, and you can see instead they have the 2-to-1 transition of hydrogen, and the nebula actually looks quite different. We can actually study different parts of the nebula by looking at different wavelengths of the electromagnetic spectrum. This is why it's so important to know all about light if you want to study cool things in space, like gas clouds and nebulae and stars and galaxies. You can break apart their light into different component wavelengths and learn about the different kinds of physics that's happening within the nebula. Very cool. This is part of the science of spectroscopy. Hello, Zachary, which you guys will be doing today. All right. As I mentioned earlier, I am sick, and I can't believe I made it through that, but I did. If you guys will excuse me, I need to rest my voice and my throat and try to get some, I just need some rest. So if you don't mind watching the pre-recorded video for spectroscopy, the one that I did this year for AS1010 is perfectly sufficient, and it's actually pretty expedient. Are you guys cool with that? Will you forgive me? All right. So do you still have the link that I sent in the chat log? All right. I'll include that in today's video clip, or I'll include that hyperlink there. Remember, it starts share screen. It starts at 140 or so. Wait, is this it? Let's just copy the paste. Shit. I think if you go to 140, all right, here's where you see it. So 145 is a good place to start, okay? All right, guys, I appreciate you putting up with me. Let me just type that in, 145 start. Appreciate you guys putting up with me. I'll see you on Wednesday, okay? Hopefully I'll be feeling better by then. Bye, guys. Take care.